taking derivative of a product. You've got all these techniques. So you learn the definition of derivative, and it's important, but I got to tell you, as you learn, especially in physics and in calculus, you know the definition of derivative as kind of an underlying concept, but most often you take the derivative through these little shortcut techniques, okay? So the power rule is a great technique. We take the derivative of sums. Today you take the derivative of a product, like, sine of x times e to the x. How do you take the derivative? All right, that's cool. You with me? All right, I'm really pumped today. I had a lot of coffee. So it would be logical, totally logical, and I definitely came to this conclusion that it's a lot like you do when you do a sum. When we did the derivative of a sum, like x squared plus x cubed, you just take each derivative, right? And so the derivative, for example, of x squared is 2x, and the derivative of x cubed is 3x squared, and as you're done. So when you take the derivative of a sum, you just take each derivative, call it good. So then when you do a product, it would be also logical to assume you do the same thing. Take the derivative of this, take the derivative of that, and there's your answer. Now I can, it'll probably be quicker just to say either yes or no. That's not good. But my goal is to make you kind of lifelong learners that allow you to figure things out on your own. And so teach you to fish kind of thing. In that sense, I would like you to think about that and investigate it on your own. Here's what I mean. Say you make up a problem that you know a product. Okay, so the question is, what happens when you take the derivative of a product? I want you to make up some kind of product problem, really simple and clean, that you could do some other way, and compare what we're talking about with it and say, does that give me the right answer, all right? So let's talk about it together. What would be a really simple product you could take the derivative of? Give me something really clean. What? Throw it out there. I mean, it can't be. X squared, x squared, x squared. Okay. Do you say we wanted to take the derivative of x squared, x squared? Do you agree that's a product? Okay. Do you have another way to do that derivative that we could check our answer with when we do our theory? What's the easiest way to take the derivative of that instead of using the product? What? Yeah. Isn't this the same as the derivative of x to the fourth? So we know our answer should come out to 4x to the third, okay? So getting into this then, all right, so we're thinking, the question then is trying our theory. Can we just take the derivative of each term separately? Does that work? Well, what's the derivative of x squared? 2x. And the derivative of x squared, again, is 2x. Now, if we then multiply our derivatives, we get 4x squared. So, can we conclude that that works? Do you just take the derivative of each piece? The answer is no, not the same. Now, as far as which one's right, this one is right. We know that's a fact. I mean, I can multiply those together and get x to the fourth. And I know x to the fourth derivative is 4x cubed. So this is correct. There's no doubt about it. This theory bombed. It stinks. Okay? So this is actually the number one biggest error on product rule is think, oh, you just take the derivative of each piece and multiply. I had a kid last year that was still trying to do that in not September, this is September. In the second semester sometime, February, he still didn't understand the product rule. It was really frustrating. So the conclusion is no, do not take the derivative of each piece. Take each derivative and multiply. And I'm sure Leibniz and Newton tried that first, and they, being intelligent people, they went through this process. Does it work? Does it check? The answer is no, it doesn't. The hard part, though, is what does work. This is actually requires a little bit of creativity. This, to me, is one of the beauties of mathematics. At our level, it's being a good analytical kind of thinker. At the highest level, like people that come up with math ideas, professors and beyond, they actually are really creative people in an analytical sense. So let me give you an example of what I mean. So they're trying to figure out how do we do this, okay? They start with, rather than that wordy kind of how do I take the derivative of a product, they make it a math idea. They would say, all right, say you make a product, how do you take the derivative? So what's K prime? You with me? Putting it into symbols allows you to use all that math skills we have. You have to, when you go about trying to develop an idea, you have to start from someplace that's accepted true. In our case, we accept that the definition of the derivative is true. It is the definition of the derivative. You follow? All right. So if I want the derivative of k prime, then this is the derivative by definition of k. If in this case k is fg, then I could replace k with fg using x plus h and x for each part. You with me so far? All right. We can all agree that's true. Now, at that point, this is when I would just say, okay, now what? I don't know what to do. Where do I go? This is where the genius comes in. Some genius, and I don't know who developed this first, Leibniz, Newton, or both, but they say, all right, this is what I'm going to do. I'm going to take this piece, and I'm going to get a little creative. And here's what they did. They say, I'm going to add in f of x plus h, g of x. Now, why they did that, I'll talk about that in a second. But let's talk breaking math. You can't just say, hey, I feel like adding something. You've got to balance it, right? And we balance math in a lot of ways. We can add something to both sides of an equation. Now, I don't want to add that to this side of the equation. I want this to be the derivative. You could also, to balance, as you add, you could balance by subtract. So you could subtract the same thing. Would you agree then that that is mathematically balanced and we have not broken math? All right. The reason they did that, and that kind of makes sense in retrospect, is I imagine when I take the derivative of this, it probably has to do with the derivative of f and the derivative of g, yeah? So they're trying to get to a place where they get the derivative of g and f. Now, I'll show you how this gets them there. Let's split this into these two pieces. Write down the no. Forget I said that, okay? Can you please forget I ever said that? That's not true. Okay? I'm going to put these two pieces together. And that would be something like f of x plus h, g of x plus h, minus f of x plus h, g of x, all over h. And I'm going to start to break this up into little compartments. That, along with the separate limit of what's left, and that is allowed. We haven't done limit rules, but it's allowed to do that. So they weren't breaking math there. In terms of what else, look at these square terms. I would have f of x plus h, g of x, minus f of x, g of x, all over h. Now, with your eyes wide open, let's see where that might get me here. I'm trying to get the definition of the derivative with maybe f and g. Do you see a derivative in here? I know it's got some extra stuff in it, right? But does this have a derivative of f or g going on here? Which one? G. This is the derivative of g with some extra stuff, right? Beautiful. So it actually, they said, hey, wait a second, I'm starting to see stuff here. They said f of x plus h is the greatest common factor, so I'm going to pull it out. And I have g of x plus h minus g of x all over h. Over here, they said, hey, that looks like derivative 2, except not the derivative of g. This over here has f of x plus h and f of x, so it's feeling more like derivative of f of x. So they pulled the g of x out front, and then they said, okay, f of x plus h minus f of x all over h. Then they had it. They said, oh, boom, discovery. This is h goes to 0. As h goes to 0, what does this approach? What? F of x, yeah? What is this approach? As h goes to 0, that is the definition of the derivative. That's g prime. First times the derivative of the second plus g of x. As h goes to 0, g of x doesn't do anything. It doesn't have anything to do with h, so it just stays g of x. And then what does this guy do? F prime. You just made the product rule. To get a product derivative, you don't just take the derivative of each piece. It's actually first times the derivative of the second plus second times the derivative of the first. Something like 1 d2 plus 2 d1 product rule results of 1 or something like that. I just made that up. It's pretty late. Don't use it. All right, but at any point, on the back side, this is the product rule in symbols. If you take the derivative of a product, it's the first function, as you see it, times the derivative of the second, plus the second times the derivative of the first. Now, say we looked back at our sample case and see, okay, is that tracking now? We said when you take the derivative of x squared, we know it should have come out to 4x cubed, right? Say we use the product rule on this thing. First, what's the first? X squared times the derivative of the second. What's the derivative of the second? 2x. Plus second, x squared times the derivative of the first, 2x. We get 2x cubed plus 2x cubed. Boom, now that's checking. And it'll check for it because it works. Okay, so that's where it comes from, which I want you to appreciate. But I used to, on a test, put a proof for the product rule. It just didn't go well. So I want you to understand and appreciate where this comes from. But I want you to mostly be able to use it. So try, say we look at this one, and then you try two on your own. So you have this function, which is a product. We could distribute, but we still have a product, so I figure might as well just keep it the way it is. You with me? So the derivative, the first stays the same, e to the x, times the derivative of the second. What's the derivative of x cubed minus 1? 3x squared plus second x cubed minus 1 times the derivative of the first. What's the derivative of e to the x? Still e to the x. And then in the e to the x case especially, sometimes in a multiple choice you'd see e to the x factored out because it's the same for both terms. But that's good for me. Try this guy, this first trig product. Ready? So you might ask, what about the 2? The 2 is a little different here. And you actually have a lot of options. You could completely leave it out front and do product rule just on the trig and have these big brackets, and that's fine. You could include it with, you can say, I'm going to call it part of the sine function, so part of my first function, and that's fine. So you have a couple different actions, and as long as you don't call it part of both, you're going to get the right answer. So, did you include the 2 way up front or part of the sine? Part of the sine. Okay. So, first stays the same, 2 sine x. What's the derivative of cosine? Negative sine. Plus second stays the same, cosine of x. Times derivative of the first. 2 cosine. Okay? So, that's fine. If you clean it up, I suppose you could have 2 cosine squared minus 2 sine squared. Any of those is fine. You don't have to clean it. Okay? Try the next one, which has, besides the derivative, then evaluating it at a point. So take the derivative in one step, keep that bar, that evaluation bar, say, I'm going to put 1 in a minute, and then in the second step, evaluate it at 1. When you have an evaluation, it should be done in two steps. The general derivative, then put it one. Don't do those two together. Question. What'd you get? 22. I concur. Okay? If you didn't get 22, check your derivative, that you used the product rule correctly, and then after that, check that you did the arithmetic correctly. I think 22 sounds right. Okay? So that's analytically, that's the most common type of derivative. We use just the equation and take the derivative using the product rule. But you also need to be able to do this in a table kind of way. Pretty common, multiple choice kind of question. So you have this table of values, and you're going to do some numerical derivative action. If you want the derivative of fg at x equals 4, then let's again, this is take the derivative, then put in the number. In two cases, do not do it all at once. So I'm saying something like, what's the derivative of fg? F g prime plus g f prime. I'm not even plugging in arguments. I'm not even saying at x. This is pretty common. Most people do this. All right. So now we're going to evaluate. The first is f at 4. What is f at 4? 2. Then g prime. Now again, that's g prime at 4. So negative 1 plus g at 4. 5. F prime at 4. Negative 3. At that point, then you're just putting it together. Negative 2 minus 15 is negative 17. Okay? Try that other one on your own. This time I'm not using g. I'm just saying x squared f of x. Because it's a product, you do have to use the product rule. You're getting something like negative 48 plus 16 for a total of negative 32. Questions? Feels like this is going okay, am I right? Okay. All right. The last one is graphically. It's not hard. Just get a little practice. Pulling information from a graph is something you have to be able to do. You understand calculus on all these levels, and graphically is one of them. So, say I gave you these two graphs of these funky looking functions f and g. You'll probably see this graph a million times. I just use it over and over and over again, including on tests. But say we wanted to find the derivative of fg at x equals 3, and I'm giving you f and g's graph. It's still a product. So start with the product rule. fg prime plus g f prime, specifically at x equals 3. Now, when you go to find f and g, you're plugging just points from the graph, right? But when you go to find f prime and g prime, how are you going to find those from the graph? The slope, perfect. Right. So the slope at 3. So f at 3 means go to the f curve, look at x equals 3, what's the y? Or here's the f curve at 3, f is 1. Okay, g prime at 3 means find the g graph, which is the red, well, yours isn't red, sorry. At 3 then, not what's the point, but what's the slope? What's the slope of g at 3? It's also, okay? When I then go to g, the next part is g, the actual curve, the actual y value. G at 3 is 3, that's the y value. And f prime at 3 is the slope of f at 3. What's the rise over run or fall over run? What is it? Negative 1/3. You agree that slope is negative for f. Okay, so we get 1 minus 1, which is 0. Okay, you try. Take the derivative of 2 sine x f of x at x equals 0 using the product rule. Okay, so first of all, do you agree with my product rule by general derivative? 2 sine f prime plus f times 2 cosine. Okay, 2 sine at 0. What is sine of 0? 0. Okay, so I suppose at that point then f prime doesn't even matter, although f prime, if you want, is negative 1/3. Yeah? Moving on to the next. What is f at 0? F at 0 is 2, that's this graph. Look at the right place, that's 2. What is 2 cosine of x at 0, or 2 cosine 0? 2. So our answer is 4. Did you get it? Okay. Well, that's it. So my question, summing it up, is when you take the derivative of a product, you just take the product of the derivatives? You do not. Okay, product goes first, comes derivative second, the second comes derivative first. Alrighty. I once again screwed up in not posting the key to the fun sheet. I worked the key, but then I forgot to post it. So I apologize. So I guess we're going to have to go over that now. We won't get as caught up as I intended, but it is what it is. So would you get out your fun sheet, please, if you don't already have it out? I'd like to at least get that turned in today, if not at 30, at the very least this week. All right? We have about 25 minutes to go over this pretty thoroughly. And if I don't get to everything, then I guess it's going to be 7th hour. The key is there now. Yes? So that's
number 11 and 12.
Yes.
It's really hard to see if it's asking for F double time or
I agree. I think they are. I went with double on 11 and what did I do on? I think triple on 12. You're right. It's a terrible copy. I have no argument with that. I apologize. Okay, so in terms of just checking your answer, and then I will be happy to make a question list in a minute, but let me first give you the answer so you know if you did well or not. Did you, for number 1, get that dy is 4e to the x? The second derivative, although it's sine of a constant, so its derivative is 0, which you didn't have to write, plus 15 halves x to the 1/2 all dx. And look at your, did you include parentheses? Because that whole quantity is times the differential dx. Yes? Number 2, This is, if you took business calculus, which is, a lot of calculus, but mostly focused on business applications, you do a ton of problems with what's called marginal cost. That's really just the cost of doing one more. The answer to that was 0.05 or 5 cents. Did that go okay? I basically did DC, which I can go back over that. For 3, my change in volume is roughly plus, and it is plus, not minus. If it's dipped in plastic, it's going to gain volume. It's not going to be losing volume. So 0.85 cubic centimeters. Is this going okay, or did you just miss it? This is a 0, by the way. Okay, we'll see. We'll go back over it, and you can figure out how things are going. In terms of the answerness, not the work, after the zeros in the sign chart, I got that this was cool for -7 to 0 and 9 to infinity. You should be using parentheses, not brackets, because log of 0 is not okay. Okay, so you should not be including the endpoints, because that would mean places where you get a 0 in the log, and that's not cool. 5, using a sign chart on that signing kind of curve, I have, this is positive, on 0 to 2 pi over 3. This one's a bit tricky with the endpoints. It is positive at 0, but it's 0 at 2 pi over 3, so that's why it is included there, but not there. Equals 0 at 2 pi over 3. 0 is not positive, so you would not include it. And, or, the interval from 4 pi over 3 to 2 pi. I had the hardest time with endpoints for those grades. I miss points on those all the time on tests. All right, B, I got this was positive. The derivative is positive for all reals. The derivative is always positive for that bad boy, which, when I thought about the graph, that actually made sense. And you never include parentheses, or never include infinity. For this, wouldn't you agree that this is the derivative of what? Sine, which is cosine. Your answer is D. The most common error on that, and that's very frequently missed on the AP test, is people say, oh, that's the derivative of sine. And so what do they circle? Sine. They didn't actually take the derivative. You actually, after you say, hey, that's the derivative, then you really do take the derivative and go with the derivative. You follow? Stop being highlighted, please. Okay, moving on to number 7, which was starting to be tangent line. My tangent line was y minus 16 equals 8 times the quantity x minus 3. This is going to be on the test. How's that going for you, the tangent line problem? Can you write the tangent line? Yes? I'm not getting a lot of, okay, you can. Thank you, Frank. Can you use the tangent line to estimate? That's skill 2. Okay. Those are the 2 main ideas. If that's not the case, then we need to work on it. All you have to do is tell me and we can work on it. For 8, this was a case where you make a tangent line, use a tangent line. The tangent line I had was y minus a half equals negative 1/16 x minus 4. And then when I put the value they want in for x, then you get B. Oui, oui. Oui, oui. All right. Back. Sure. Feel free to write these in ink if you want to make corrections and ask questions. Or
Is that negative 1 over 16?
yes. Okay. Moving on to this bad boy. It's a little ugly. Actually, if you were a calc honors kid, you probably could have taken the derivative of that with the chain rule, but we haven't done the chain rule yet, so that's why I said you can use your calculator. So that said, then the point was this. Don't confuse the point you're trying to estimate with the point at which you do your tangent line. You're supposed to do the tangent line at 0, and what do you get when you put 0 into that? 1. All right, so that's the point of tangency, not this. We're going to put that in later. The slope is the derivative of that bad boy in your calculator at, again, the good point, not at point 1, not at negative point 1. And hopefully you got something like, what'd you get there? Negative 1/2? Yes, does that sound right? No? Yes? Okay, so the tangent line then is y minus 1 equals negative 1/2 x minus 0. So if you then use your tangent line with an x of negative 0.1 in it, you get y is 1 minus 1/2 of negative 1/10 minus 0, which is d, which is actually 1/120th. Right? Okay, 10, this requires you to make a verbal connection to calculus. Okay, so there's all the meshing of the levels of math, verbal, analytical. The curves have parallel tangents. Tangents mean derivatives, yeah? Parallel means same slope. So parallel tangent means derivatives are the same or equal. So you need to find where the derivatives are equal. So take their derivatives. You're going to take, where is f prime equal to g prime? The derivative of f is 2x minus 5. The derivative of g is negative 2. So you get that this happens at an x of something, 3/2. Yes? This was bad. This had two problems. First of all, hard to read. Second of all, algebra. Oh my goodness, the algebra was a stinking nightmare, wasn't it? It was awful. This book is, this is like a test prep book I pulled this from, and it is known for its terrible algebra. The derivative is nothing. It is so easy. The derivative is, if this is 4x to the half minus 16x to the fourth, the derivative is 2x to the negative 1/2 minus 4x to the negative 3/4. That's the first derivative, right? So the second derivative is negative x to the negative 3/2 minus plus 3x to the negative 7/4. Do you first of all agree with my second derivative in its cleanest state? All right, so then the algebra. Boo. I went and said, okay, it's obvious I have to clean this up. So I called this negative 1 over square root of x, or actually x to the 3/2 plus 3 over x to the 7/4. First step, I just said, all right, let me call those negative exponents reciprocal. You cool? They obviously put their answers together, looking at their answers. So common denominator, common denominator, it helped me to start by calling this x to the 6/4 plus x to the 7/4. Isn't 3/2 the same as 6/4, yeah? All right, so then common denominator. Is it 6/4, 7/4, 13/4? What do I do? 7/4 is the common denominator. I need then another fourth here, so I need to multiply this by x to the 4th. So this will be negative x to the 4th plus 3. Now I'm starting to get somewhere. Still don't really see it. X to the 7/4. I'm going to call this x to the 4/4 and x to the 3/4. So then, you might see it from there. x to the 4/4 becomes x. X to the 3/4 is the 4th root of x cubed, and so our answer is E. And boy, did you have to earn it. All right. This, if you were able to read my key, I actually put triple prime, question mark. I went with triple prime, and if you went triple prime, the answer is 5 times. Cool? When the velocity of the car is positive, wouldn't you agree that the velocity is the first derivative of position? So you should have taken the first derivative of position, then set it equal to 0, do a sign chart, and so velocity of the car is positive on, did you say, negative infinity to -1 and 1/3 to infinity. Now, you physics people say, oh, it's a negative time, that's stupid. In calculus, negative time, no problem. Yeah. Okay, why not? It's all relative, right? Who's to say this right now isn't time 0? Was there time before this moment? Yeah, there was, maybe a time, maybe. So, yeah, it's kind of relative, but Mr. McAllister would probably bristle at that. And math, it's fine. Sometimes they'll say only time positive, and that's fine too. But if they don't say, all reals. When is the acceleration of the car positive? Again, in calculus class, especially in my class, if I say acceleration, that's implied positive acceleration. And if I want to say negative acceleration, I'll say deceleration. That's not necessarily the case in physics. Again, I apologize, but you're just going to have to get used to it. There's going to be some switching of modes when you go from one to the other. Anywho, the acceleration is a change in velocity, so the derivative of velocity, which then would be the derivative of the derivative of position, so the second derivative of position. Either way, you again need to find the second derivative, set it equal to 0, sign chart, and so you should end with negative 1/3 to infinity. Again, I'm not including endpoints because the velocity is not positive there, it's 0, and 0 is not positive. All right, thank you. Okay, so set 26 then. Okay, I tried. This is going to be a lesson we'll hit later, but it really takes a while to get into the thought process. This is one of those calculus ideas where you have to think a certain way. And I'm trying to start a little earlier because I feel like it takes really a month or two before it's just automatic. So this is the thought process. I tried to get you some instructions. As clear as I can possibly make directions, they're limited in the fact that they're only useful if you read them. Okay? If you just say blah, 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 words, blah, 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 there's problem 14, here I go, well, then that's wasted. That's wasted information for you. So my suggestion is you start by reading. They might be handy, you never know. So here's the deal. Where the tangent is flat and therefore horizontal, well, that means the derivative slope is 0. So the graph of the derivative will be at the x-axis. Here's what I mean then. Say, look at this graph. The slope is 0 right there. So that means if I were to do the derivative on the same graph, the derivative would be 0 at that point. Also, if I did slopes over here, where the function is increasing, you can see those tangent lines will be positive slope, which means the derivative is positive, and therefore the derivative graph will be above the x-axis. So I'm going to get positive slopes here, so everywhere on this side I'm going to get positive derivatives. Then I get negative slopes because it's decreasing, and so the derivative will be negative. I'm looking for a graph like that, and that is, hey, that's 3. Okay, that's the derivative graph for that function. This is the derivative ever zero here. Is the slope ever zero here? No, it's never zero. In fact, it's constant. It's always the same slope. So the derivative of this is, which one of these is never zero? The first one. Okay? The slope is always 2, whatever that is. Okay? This then, flat 2 places. So there should be 2 places where the derivative is 0. I'm looking for a graph with 2 zeros, so 2 x-intercepts. That right there tells me this guy. Furthermore, positive above the x-axis, negative below the x-axis, positive above the x-axis. This is just screaming 2. Let's check this on a second level here. Think about this. What shape does this look like? X cubed. What's the derivative of x cubed? 3x squared. Parabola. Derivative of a cube is a parabola. That makes sense. Okay? Then finally, this guy. How many times is the slope 0? Well, it should have 1 0, positive slope, positive derivative, negative slope, negative derivative. That is also this guy. Now, the obvious question to this would be, what the heck? How can that be the same derivative for both of these graphs? How are these graphs different? It's the same shape. They're different by virtue of a constant. And if you take, say you had x squared plus 1 and x squared minus 4, take the derivative of each, the derivatives are exactly they're the same. And so that constant doesn't affect the shape or the slopes of the derivative. You'll see that 2 functions can be funneled into the same derivative based on the constant just going away. That happens. And tomorrow when we take the antiderivative, you'll have to remember that. All right. Set 49. Number 49. Sketch the graph of f prime given f. So I'm just going to say, what's the slope? What's the slope here? 0. So the derivative will be 0 until 3. At that point, then, 3 starts to get funky, so I'm just going to put a dot there because 3 is its own little thing. It's called differentiability. We'll go there later. How about in here? What's the slope from 3 to 5? Rise 1 over 2, it's 1/2. That means the slope is 1/2 constantly till I get to 5. Then 5. Things start to get a little funkier. Do the slopes, are the slopes positive or negative? Positive until I get to 7 where the slope is 0. So what do I do now? Let's start with 7. So at 7 I should put what? An x-intercept because the derivative is 0, right? What about from 5 to 7? The derivative is positive. The question now is, what shape do I make? I don't know what shape to make. Well, what's the derivative of x squared? X. So shouldn't it be linear? So I'm thinking linear. Now, how steep, that's kind of gray area. But linear seems logical. What about over here? Slopes are negative, so derivative should be negative, therefore below the x-axis. Okay? All right, 71, A through C, matching. Here we go. So I started with 0 slopes, okay? So for this guy, I said, all right, I've got a 0 slope there, there, and there. I need something with zeros 1, 2, 3 places. Which of these has 3 zeros? 3. Okay, so this feels like a good candidate. If my life depended on it, I would probably then go a little further and say, what about positive, negative slopes? Isn't this positive slope here? So the derivative should be above the x-axis. Cool. Negative slope here, so the derivative should be below the x-axis. Cool. Positive slope above the x-axis, and then negative slope below the x-axis. This is tracking to 3. Okay, let's go here. How many places is this flat? It's easiest to just say, where's the derivative of the slope flat as your starting point. How many places is it flat? 1. That means you should have a graph of a derivative with 1 x-intercept. Which one fits the bill right away? 1. You also would agree it has the right positive, negative behavior above the x-axis, below the x-axis. So this is 1. We. Last but not least, how many flat spots here? 2 flat spots. So I should have 2 x-intercepts. That means this guy, positive above the x-axis, negative or decreasing below the x-axis, increasing above the x-axis. So that is. And then the hardest one for me was the last one. I don't know about you. This took me a while, and I erased what I did. I screwed it up. I wasn't quite sure. I wasn't even quite sure I understood what the question was asking and how to label stuff, but I eventually figured it out. So I need to figure out which is the original, which is the first derivative, and which is the second derivative. At the end of the day, that's really what the question is, which is the original, first, and second derivative. You cool? Okay, where I'm saying the original, based on what I'm seeing, the original is h, and g is the derivative. The first derivative is g, and then the derivative of that is that right? G's derivative, f prime is, so if I took the derivative of d, wait a second, that's not right. See, I have the same issue again. Doggone it. I'll tell you what my answer is, and then we can talk about it. How's that sound? I had that this was f, this is h, and this is g. What do you think? Okay, so I got some yeses, so I can't do that. Or maybe we all just. So actually, the first thing, this is probably, especially starting out, probably a bad question because this is starting out new hard enough without having to get through a bad question. In fact, maybe we should just scrap it all together because the question's not working. Do you understand the ideas that we were? Okay, let's stop. Let's call that good. Okay. I didn't feel like this question was worded very well, so I probably will dump it next year. Don't worry about it. Anything I can talk more specifically about on this that I didn't get through thoroughly? Okay, so this can we do by the end of the day? Okay. 30 we will get to. So if you have a quick question on 30, I could maybe throw it up. But I did not even make a key yet, so never mind. Oh, man. Oh, well. Okay, so set 30 is not due today. The fun sheet is due today. Is that clear? Cool. Hey, you have a, you have a lockdowny thing, right? 6th period today, 1:15. So take your math to 6th period. Take to get a chance to look at your math. Alright? I think the plan is you just stay in 6th period for 7th hour. Yeah, that's it.
You're both at question at 12. So we moved to the group, we got 60 x squared, keep mine 60, so it's going to be negative 60.
No one's going to so did you say where is this?
Zero with.
No, that's not the question. The question, it doesn't say what is f triple at 0. It says find when f triple is 0, and then plug that in stuff. So you're reading it as this. Okay. question. You're doing a good job of being involved. You're doing a good job of talking class and asking questions. Keep up the good work, buddy. No, thank you. It's my job a lot easier. You do not have a 7th hour.